Hey guys, in this video today I'm going to be analyzing the calculations behind the ball rolling down an inclined plane. The calculations you'll be seeing was done by my teammate Bashar Yaqub Agha and it's going to be analyzed by myself. The parameters of these equations are going to be as follows: the normal reaction on the sphere's angular acceleration, angular velocity, the velocity and acceleration of the sphere center point C, and lastly the friction force between the sphere and inclined plane. These parameters can be seen here on the left in this free body diagram, and the original diagram can be seen here on the right. So some variables that are going to be seen in the following equations can be m, capital R, theta, and so on and so forth. All these variables refer to different values, such as the acceleration due to gravity is referred to as lowercase g. So the equation of the normal reaction on the sphere is mg cos theta, as you can see here. The sphere's angular acceleration, angular velocity, considering there's no slipping and the ball is just rolling, the sphere's angular acceleration and angular velocity are related to the linear acceleration of the sphere's center of mass and the radius of the sphere by this following equation. The velocity and acceleration of the sphere's center point C, the linear acceleration A, and the velocity v of the sphere's center point C can be determined using the inclined plane's angle theta and the net force acting on the sphere, as you can see in these three equations over here. So the equations for static friction are shown here, and the equation for kinetic friction is shown over here. So the moment of inertia of the sphere is shown here. It's not going to be used now, it will be used later on in the video. So these are the equations for calculating the critical angle that leads to slipping. And this is a continuation. As you can see, we have a final expression for the critical angle. So to test if our equation is accurate, we have subbed in values and we're going to be comparing this to the MATLAB version. As you can see here, the equation for the moment of inertia of a sphere is finally used. So after subbing in the values into MATLAB, we get a critical angle of 60.2551 degrees, and we have with our expression we have an angle of 66.17 degrees, which is fairly close. The only difference is if we increase the angle phi to 55 degrees, the radius to 2 meters, the mass to 1.5 kilograms, and the static coefficient to 0.4, the MATLAB outputs a result of 54.4623 degrees, whereas our model outputs a result of 54.189 degrees, which is fairly close, proving that this equation here is fairly accurate. Thank you very much for watching our video. I hope you enjoyed and I hope you learned something. Have a nice day.